Hello, in this video we are going to discuss about electric charges and also the topic under which they are vastly studied, that is electrostatics. And it is believed in about 700 BC, a Greek philosopher by the name of by the name of Thales of Miletus, he had found that when amber is rubbed with say cat's fur, it started attracting lighter objects. So let us say pieces of paper, after it has been rubbed with the cat's fur, it started attracting pieces of paper, just like the case when you observe that you have a plastic comb, or and you rub it against your, or you brush your dry hair with those plastic comb with that plastic comb, and you start to bring it near pieces of paper, torn pieces very small, it starts attracting them. So he also observed somewhat like that. And then again, come to around 2500 years later, at around 1600 AD, you had the personal physician of Queen Elizabeth by the name Dr. Gilbert, and he also observed similar cases when other materials such as glass and ebonite and then sulfur and all of these, when they were rubbed with various materials such as wax, and even the case of silk probably, and when these were rubbed against such materials, then they started attracting pieces of paper as well, or lighter pieces. Now, such property that was obtained, well, amber in Greek, the amber material that in Greek is called as electron, that it is K. So from that we have the word electricity, because this phenomenon then was termed as electricity from the word electron. And then it was again because the friction with all these things led to such property of electricity, it was termed as frictional electricity. And then obviously the charges that were studied, they were under rest. So the charges were under rest, and that is why it is a static electricity, or put together as electrostatics. Now, in this video, we'll be studying about the static charge, its behavior, and gradually, as we will be doing a series of video on electrostatics, we'll be knowing more about how they apply forces, the magnitude of the forces, the field around them in which they can impact other particles which are in their vicinity, other particles meaning other charge, because the forces that are observed are usually between two charges. Even if you see the case where the bits of paper, they may not be having any charge but they are still attracted, we'll know why they are attracted in such a manner. Now, coming back to the case of frictional electricity that we have just studied, frictional electricity, well, you can consider the case of an atom. Now, the atom comprises of a centrally placed nucleus, and around that the electron orbits. Now, there's a simple structure of an atom, say a nucleus with an electron, and the electron that I have considered in this figure is probably the outermost electron. and it is this outermost electron which has a fair chance of getting detached from that atomic structure, because this is pretty loosely bound. This is loosely bound as opposed to the other electrons which are in the inner circles of the atomic structure. So this being loosely bound, it has a fair chance that some force, in this case this is the frictional force, that force is quite uh, sufficient to knock this electron out of that orbit, and this electron in turn gets stuck to the other object with which the frictional force has been generated. So take the case of glass and silk. So in that case, the glass, when rubbed with silk, one of the electrons from the glass, that the outermost electron in the atom of the glass, that gets knocked out and that gets stuck to the silk which is rubbed against the glass. And as a result of that, the excess of electron in silk causes it to have an extra negative charge, while the loss of electron in glass, that causes it to have a positive charge altogether. So, and as a result of that, these charges, they start attracting each other. Now, as for the case of charge, what does that mean? Because we have started off with the topic of electric charges. The charge is a characteristic, it's an intrinsic property, just like the case of mass possessed by an object. So is the case of charge possessed by an object. Now, the charge are basically of two types. We have the positive charge, we have the negative charge. And as you can see from the atomic structure, the positive charge is due to the protons which are present within the nucleus. The nucleus carries the protons which are tightly bound inside the nucleus, and they are positively charged, while the electrons that are revolving about the nucleus, they are carrying a negative charge. Now, the case of an atom, it is electrically neutral most of the times, until and unless some external force has knocked out the electron, just like in the case of frictional force knocking out the electron. By nature, the atom is electrically neutral, and as a result of that, although they have the charges, the substances, they are composed of atoms and molecules then further divided into atoms. So these atoms, although they have charges, but the charges that are present within the nucleus as well as outside in the form of electrons, the negative charge, they are equal in number, and that is why the atom as a whole is electrically neutral even though it carries charges. Now, charge being an intrinsic property, it is responsible for such electrical effects as well as magnetic effects. We'll be learning about the magnetic effects of charges later on, but it is responsible for such electrical effects. The sensation of mild electric shock that we feel while turning on a tap or a door, or the crackling sound that we hear when we take off the pullovers or the sweatshirts or the clothes during the winter, they are all because of such electrostatic charges that are present around us, that they are built up because of the friction between two surfaces. The metallic bodies of vehicles are also charged due to friction with air, and as a result of that, that is why, so that they may be carrying explosives, the vehicles which carry explosives, they are provided with chains which are hung from them onto the ground, and then we are safe in that respect. There is no charge built up, and there is no problem with the explosives that is being carried in those metallic vehicles. So the danger is averted in that case. Now, the also the case of the positive and the negative charge, it was coined by Benjamin Franklin, the American scientist. He named those charges as the positive and the negative charge. So This is credited to Benjamin Franklin. Now, all of that, the case of the interaction between these two charges, let us say the case of positive and negative charges. Now, it has been observed that the like charges, they tend to repel each other. They provide a repulsive force on one another, while the case of unlike charges, that is the positive and the negative, like charges as in positive positive or negative negative, unlike charges, that is one positive and the other negative, or vice versa, that is the negative with the positive, they always attract each other. So the force is always an attractive force between them. Now, the property which differentiates the two kind of charges is obviously the polarity of the charges. We'll say that a body which was initially neutral, probably the case of an atom, when it loses an electron, then it gets positively charged. It's a positive ion now, and it has achieved a positive polarity. And then if there is some excess of electron on any body, just like the case of silk over here that I mentioned, silk being negatively charged upon receiving an electron from the glass atom, so that becomes negatively charged. So addition of electron, because the electron is the only thing that is free and that can move. The proton, on the other hand, that is usually bound within the nucleus, so it's very difficult to get a proton or a positive charge out of somewhere. So the electron is one which is lost from any given object, or it is gained by a certain object to get negatively charged. So it achieves a negative polarity when it receives an electron from other sources. So whenever it comes to the case of a body carrying some amount of charge, let us say a body has 10 coulomb of charge and another body has a minus 10 coulomb of charge, we may be asked that which of these bodies has a greater amount of charge. Well, in that case, if we are comparing it in terms of magnitude, obviously the charge is the same. The magnitude of charge is same. But the case of polarity is different. One of them is positively charged and the other one is negatively charged. But if one further inquires about the amount of charge or the number of particles involved in achieving that amount of charge, well, that will be different, because this will be devoid of some electrons. The electrons would have gone out of it, and that is why it has achieved that amount of charge, while some electron might have been added. Definitely they would have been added. There's no case of may or maybe. There will be some excess of electron in this case, that it has achieved such a negative charge, and there will be some loss of electron from the first body, that is the positively charged body, and that is why it is positively charged, just as we saw in the case of the atom, or even the case of the glass and silk example. Now, that will be discussed later, that how many electrons were lost or how many electrons were gained in order to achieve that positive or negative value of that magnitude, that is plus 10 or minus 10. We'll be knowing that, we'll be dealing with that in the quantization of charge, which is later in this series. Now, with the electric charge being a physical quantity, we can have certain unit and dimension associated with it. So usually the electric charge is represented by the letter Q. So a charge Q will have a unit which is coulomb, which is what I have mentioned over here already. So coulomb is the unit of charge, usually represented with a capital C. And as far as the dimension is concerned, now this charge is a derived quantity, it is not a fundamental quantity, and that is why it needs to be mentioned, or it needs to be written in with the help of a few fundamental quantities. Uh, we know that from our basic studies in the junior classes that the current is actually the amount of charge that is flowing across a conductor divided by the time taken, and that is why, and the current has a unit of amperes, while the charge obviously has the unit that we mentioned over here. The time is in seconds. So now if we are to give the dimension of charge, it will be having the dimension of these two physical quantities, that is the fundamental quantities, that is the current, whose dimension is usually written as A, and sometimes it is taken as I as well. And as for the time, it has the dimension T. So A1 T1 is the dimension of the electric charge. As for the unit coulomb, it is the standard international unit. We also have the CGS unit, and it's in two ways. This is the electrostatic unit, and then we also have the electromagnetic unit. Because I said that the charges will be involved both in electrostatics as well as in magnetism, so we'll have two separate units in the CGS system. The electrostatic unit being stat coulomb, while the magnetic unit is ab coulomb. We'll relate the electrostatic unit, that is stat coulomb, with the SI unit, that is the coulomb, further as we discuss. In one of those examples, I'll be discussing about the relation between them. I can, however, give you the value right now. 1 coulomb is simply equal to 3 times of 10 raised to the power 9 stat coulomb. As for the ab coulomb part, well, the ab coulomb is 1/10. So 1 coulomb is 1/10 of an ab coulomb, but that is in the electromagnetic unit to be dealt in magnetism. We'll deal with it later. This value that I have just written, that is 3 times of 10 raised to the power 9. In one of those examples that I'll be doing, I'll be giving you this, I'll be proving this to you. Now we shall discuss about the properties of charge. First things first, charge is quantized. Well, that means the charge exists as a quantity, and the amount of charge that we obtain, be it positive or negative, is actually a multiple of that quantity, and exactly an integral multiple. It cannot have any fractional value. So let's understand what exactly are we discussing here. Now take the case of the atomic structure, and the atom is formed or composed of the nucleus and the electron revolving around it. The nucleus carries the nucleons, which are the protons and the neutrons. Now the protons and the neutrons, the proton carries a positive charge, while the neutron carries no charge. It is electrically neutral, so we can say the charge here is 0, while the electron that is revolving around, that carries an equivalent amount of negative charge as that of the proton. Now these protons, neutrons, which are collectively called as nucleons, lying at the center, they are composed of materials called quarks, while the electron is a lepton. So these are made of quarks, while the electrons are leptons. Now the quarks, if we go over to understand them, they are quantities which have fractional charge. The quarks have values of charge as let's say plus 2 by 3 times of E, or even minus 1/3 of E. E, the number that is associated with that value E, is what we'll be writing down later. But as of now, just we need to understand that the quantity that we were talking about, the quantity that exists, the minimum value of that quantity is E, and whatever the charge is possessed by any of the object in this universe, that is an integral multiple of that E, that is Q, which is the charge that is carried by a given object, is equal to n times of E. And that is what quantization is all about. But here what I am saying is that the quarks, they have a charge of plus 2 over 3e or even minus 2 over 3e. We need not go into detail of what kind of quarks, but there are plenty of quarks. We are just concerned about the up quark and the down quark, which make up the protons and the neutrons. So in case of proton, well, the charges that are possessed by these quarks, however, the quarks do not are not present in a single form. They always form groups. In this case, they are in groups of 3. In case of the formation of the protons and the neutrons, they are in groups of 3. So for the proton, you have 2 up quarks and a down quark making up the structure of the proton, or giving the charge to the proton. If you go on to calculate this, then you have plus 2 over 3e, plus 2 over 3e, and minus 1 over 3e for that d, for that single d that is there. So here you have plus 2 over 3 plus 2 over 3, that is plus 4 over 3, minus 1 over 3. So that gives me plus 3 over 3, that is simply E, and that's positive. As for the case of neutron, you have 1 up quark followed by 2 down quarks. It does not necessarily follow in that sequence, but they are combined in that sense that you have U, D and D. So you have plus 2 over 3e, that is the value of U, that is the up quark, and then you have the down quark, which is 1 over 3e and 1 over 3e in negative. So plus 2 minus 1 all over 3, that gives me 0 over 3, and finally you have the value to be 0 times of E, or simply 0. In case of electron, it is just the other way around. It's not formed of quarks, obviously it's leptons, but still it has the charge of minus E. The electron has the charge of minus of E in that case. So this is how they are combined. So as you know, in nature, the minimum value of charge that we can have is either plus E or minus E, that possessed by the proton in this case and the electron. You have also the positron, which is the antimatter of electron, that just has the same mass as that of electron and the opposite charge. The proton is not the antimatter of electron because the proton has a different mass as that of electron. Proton is 1836 times heavier than the electron, so it cannot be the antiparticle of electron. Now as we know that the minimum value that we can have for the charge is that value E. The value that is associated with E is 1.6 times of 10 raised to the power minus 19 coulomb, which means that you cannot have any value which is less than. Sometimes in some places you can have a value 1.59 times of 10 to the power minus 16 coulomb. Well, 1.59 just rounded off for calculation is 1.6, but that is a different thing. But you cannot have a value which is less than these values. The electron and the proton, they possess this magnitude of charge. And as we know that electrons are fairly easily available, so the electrons make up for the positive or the negative charge possessed by any given object. The loss of one electron would result in that object having a positive value, that is plus E, that is 1.6 times of 10 raised to the power minus 19. An addition of electron, on the other hand, to any given object will cause it to have a charge of minus 1.6 times of 10 raised to the power minus 19 coulomb. So this is what we see, or what we learn about the quantization of charge. Suppose I say that let me just consider a problem over here. It's not necessarily Q, that means the question over there, not the charge. So can an object or a quantity possess a charge, let us say 12 into 10 to the power minus 20 coulomb? That's the question. Well, let's check that out, because we have the value of Q over here. From quantization, we know that Q is equal to N times of E. Here the charge is Q, and Q is given to be 12 times of 10 raised to the power minus 20 coulomb, and we have a value N over here, which is an integer, and E is the charge of the electron, or let us say the proton for a positive charge. So we have 1.6 times of 10 raised to the power minus 19. To find the value of N, we just divide it onto the other side. So 12 divided by 1.6, this is 10 raised to the power minus 20. This is 10 raised to the power minus 19. And what does that leave us with? Well, that is 120 over 16, and this is 10 raised to the power minus 1. 10 raised to the power minus 1, that simply cancels out with that. So this is 0.75. Now this is not a whole integer. This is a fractional value, 3 over 4. The electron or no quantity can have a charge which is less than the value of that. Now this is a number, that the number cannot be a fractional value. That is what we are trying to discuss over here. The number cannot be a fractional value. It has to be a whole value, either 0 or 1 or 2 or 3. It goes on like that. Not even negative value. The negative value is possessed by that charge E over here, that is either plus E or minus E. Depends on what kind of charge we are dealing with. Either we are dealing with a positive charge or a negative charge. Here in the question we had the positive charge, so we have the value of this, we have this value to be positive as well. But the case is, the concern is over the number that is N. The number N will have whole values, that is 0, 1, 2, 3, 4, 5, and it goes on like that, right up to infinity for a greater amount of charge. Now from this also, what we can say, that what is the charge possessed by just 1 coulomb, or what is not the charge, I beg your pardon, what is the how many number of electrons? Let me change that question for you. How many number of charged particles, be it electron or proton, let me erase that completely for you. So how many, let's take electrons. Electrons make up minus 1 coulomb of charge. Obviously electron carries negative charge, so that is why it will contribute to a negative charge as a whole. So from quantization we know that we have Q is equal to N times of E. Q here is equal to minus 1 coulomb and N is to be obtained. E in this case for electron that is making up the charge is minus 1.6 times of 10 raised to the power minus 19. N will therefore be equal to, and this is in coulombs as well, so the coulombs, the units are gone, we just have a number associated, and the negative signs can be taken care of as well. So we have N to be equal to 1 over 1.6 times of 10 raised to the power minus 19, and that goes up, so we have 10 to the power plus 19 divided by 1.6, and 10 over 1.6 is roughly equal to 6.25, so that is 6.25 times of 10 raised to the power 18 number of electrons making up that negative 1 coulomb of charge. So a unit value of charge. Now if we were to say that how many electrons were involved in obtaining plus 1 coulomb of charge, the object in that case would have lost that many electrons, that is 6.25 times of 10 raised to the power 18 number of electrons would have been lost by the object or from the object in order to achieve a plus 1 coulomb of charge. It is usually the transfer of electrons because, as I said, the protons are deeply bound within the nucleus, so they are bound by strongest force in nature, that is the nuclear force there. So it is highly unlikely that any kind of charge has occurred or any kind of charge has been possessed due to transfer of protons. Protons do not usually transfer from one body to another body. It is the electrons which are loosely bound, the outermost ones. They are involved in carrying the charges. As I said, loss of electron, positive charge; gain of electron results in a negative charge altogether. So that's it from this video. We'll be dealing with more such properties. To name a few, we'll be dealing with the conservation of charge as well as the additive property in the upcoming videos. Till then, thank you for watching.